Welcome. In this lecture, we're going to do an exercise on temperature drop calculations in the wellbore. The main goal of the exercise is going to be to calculate the temperature along the vertical well, from the bottom hole all the way to wellhead. For that, we're going to use the file that we have used earlier, in which we have done our pressure calculations in the tubing. But we're going to use a kind of a simplified version of that sheet. We're not going to look into the effect of different models. We're not going to use different correlations for the void fraction. We're simply going to use one. So we're going to use the drift flux model and with the Volga correlation for the void fraction. I made also a few other changes, like I added here the density at standard conditions of oil and gas. We will see later what we need that for. And also the BO tables, they are updated because now we need the enthalpy of oil and enthalpy of gas, which we didn't have before. And the properties will be slightly different because I'm using a composition which is a bit different from the one that we have previously used. But the whole sheet should be very similar. So we had, in terms of temperature, what we did at that time was we set the wellhead temperature. We have the bottom hole temperature, and we simply did an interpolation, linear interpolation for all the points in between. And that's how we find the temperature. We assumed that this was an input, and then we had the pressure at the wellhead, and then we calculated all the conditions at the wellhead. We calculated the void fraction with the correlation from these two researchers, and then we calculated the pressure gradient at that position. With that pressure gradient and using an explicit integration, so then we calculate the pressure at the low 500 meters below by saying that is the pressure 500 meters above plus the pressure gradient times the distance. Okay, and the pressure gradient was calculated using the drift flux model and neglecting the acceleration pressure term. So we're going to use that sheet, and you see here to the right, I have added a few columns that we're going to make our temperature calculations. So the first step is to now these values they're not going to be calculated, but they're going to be assumed. So we're going to change the color code to violet just to make sure this is to say that this is assumed. And then we're going to paste this also has a number, so it won't be an equation, and that will be also in violet to indicate that they are assumed. So now we want to verify if these numbers make sense regarding the energy conservation equation, and if they don't make sense, I want to change them to make sure that they make sense, that the energy balance is satisfied. So now that we have assumed, at least we have assumed some temperatures and pressures, well, we can calculate the enthalpy of each point. Okay, the mixture of the enthalpy, specific mixture enthalpy. And if we take the notes from last time, okay, remember that the enthalpy of the mixture is the mass fraction of the gas times the H of the gas plus the mass fraction of oil times the H of the oil. So we need to calculate two things. We need to calculate the enthalpy of gas and enthalpy of oil. We don't have any water in this case, so we don't need to take care of this term. And then we need also to have the mass fraction. So for that, let's calculate first the enthalpy. Enthalpy is in this table here, and it's in column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 12 and 13. So remember last time we put here the number of the column. So with this one, HO and H gas should be in 12 and 13. And we can probably just copy this expression and paste it here. Maybe we can simply copy like that. And it's using that column. And we want actually the table here is not all the way until K, but it should be all the way until M. So here we should change to M because enthalpy is actually in M. Okay, but all the rest should remain the same. Okay, we delete here. And that number is in kilojoule. We have to be careful with the units, but it's in kilojoule per kilogram. Now we drag it up here and then we Okay. Now let's calculate the mass flow, the mass fraction of gas. But first, let's calculate the mass flow going through the tubing, because that will be the denominator we need to use here. The mass flow, that's constant for all the sections, the total mass flow. And then we need to find the mass flow of gas for each position. So let's do that. The mass flow, total mass flow, it's the rate of oil times the density of oil at standard conditions, plus the rate of gas at standard condition times the density of gas at standard conditions, and then this is going to give in kilogram per day, and then we convert from day to second, which is dividing by 3, 600 times 24, 11.3 kilogram per second, circulating through that wellbore. So then to calculate the mass fraction of gas, we're going to take the mass rate of gas at that position, so that will be the Q of gas times the density of gas, which is here. And then this will be in units of kilogram per day again, so then I have to divide by and convert to seconds, 3600 times 24. And then I divide that by the total mass flow. So that's how I calculate the mass flow of the mass fraction of gas. Then I divide by this number, and then I have to block this number. And you see it goes from 11% at the top all the way to 5% at the bottom, which kind of makes sense with the PT diagram that initially I am closer to the liquid, so I should have less gas. So this is 5, and then I go down here, I have 11%, and then I have more gas. Also note that this PT diagram is different from the original file because I changed the composition, and then now the fluid before I found undersaturated oil at the bottom of the tubing, but in this case I don't have that anymore. Now the enthalpy of the mixture will be X of gas times the enthalpy of gas, plus I need the mass fraction of oil, which is simply 1 minus the mass fraction of gas times the enthalpy of oil. Okay, because I have very little gas, then the enthalpy will be very close to the enthalpy of the oil, not to the enthalpy of the gas. The temperature of the formation, we have 100 at the bottom hole, and then we will assume we have 20 at the surface. We are maybe in a tropical country, so we have 20 degrees, and then we simply do an interpolation between these two conditions. So I have the X, that will be this X, I block it, then I will be this, then I have the other extreme, which is the other X, and then this temperature, and then I have the X of that position, which will be here. Then I get 31, and I get 89. The U, the overall heat transfer coefficient, we're going to assume a value of 9, and we will take a look at in a later video where that number came from, but we're going to assume for now is constant. Although you might think that if on all the different sections we have different layers between the fluid and the formation, depending how many casings we have and how many cement layers we have, so this might change also along the wellbore. But in this case, just to keep our calculation simple, we assume that we have a constant number. Now the next step, so now we have calculated the H in each position, right, in and out, and now we can to calculate the heat. And then what we are going to do is we are going to apply somehow the energy equation to find out the temperature, okay, or to find out if if those temperatures that we assume they're actually correct. If this energy equation it is satisfied. Okay, but let's calculate now the heat, and the heat we're going to do it in two steps. So first we're going to calculate the heat, the dQdL at a given position, at a given set, and that will be minus 2PR, the U of that place, and then the difference of temperature at that place. Okay, so that will be this column here. We're going to calculate at each position the dQdL. So that if you punch Alt F11, you will see we have on the modules, you have one called heat transfer, and then we have one function called dqdl, which is exactly that, the pi diameter, this is 2r, and then we have the u of that section, and then we have tf minus t ambient. And this has a proper sign, which is saying that if it's leaving, so it's going cooling the fluid, then it's negative, and if it's heating the fluid, then it should be positive. In this case, according to the sign, here it gives you that is 0 for the first point, but for all the subsequent points, always this temperature is greater, I think, than the temperature of the formation. So then we should have cooling, and then this dqdl should be negative, I think. Okay, so we have a u, and then we have the diameter. Diameter is someplace up here. Then I have the temperature of the fluid, not the formation. Temperature of the fluid is the one we have assumed before. And the temperature, ambient temperature, or the temperature of the formation, is this one. And you see the number we get is negative, all the way to 0. Now to calculate, that's the Q at one particular position. To calculate the Q at, of the section, and here the section, we're going to say the section is the section 1. I'm going to write it here, and that will be the heat that is exchanged in this, between these 2 points. And then the section 2 will be between these 2 points, and so forth. Okay, so at the end we don't have to go all the way here, because when we reach already here, we will have this section, and that's the last section of the wellbore. So to estimate that heat, I have the dqdl at 2 positions, one here and one here, and I can simply do an integration along the set just to find out the q. And I'm going to say that integration, I do it using the trapezoidal rule. So I have the value here plus the value there divided by 2 times the difference in x, which is delta L. So that's the equation I'm going to use to approximate the heat on the section. So that will be this one plus this one times 0.5 divided by 2 times the delta L, and the delta L should be positive. So then this one minus this one, then I close, and I should still keep a negative number. So you see that for lower sections is relatively small, but for higher sections is relatively high. So the next step I'm going to say, well, I already have everything that I need in this equation. I have the Q, I have the 2H, and I have the elevation. But I don't know if the temperatures I assumed is satisfy this equation. So I'm going to call something called residual. I'm going to put everything on the equation on one side. Okay, and then I'm going to say this is going to be the residual of the energy equation. So it's going to be simply putting everything to that side. Okay, and that equation is also programmed for you in VBA. So see, the residual of the energy equation is enthalpy in. Let's maybe just make sure that it makes sense. Enthalpy in minus enthalpy out. It should be +1, right? I guess here is also +1, yeah. So enthalpy in minus enthalpy out minus delta set. Set here is the out minus the in plus the Q. And the Q here has negative sign. Okay, so it's exactly that, is the residual of the energy equation. So I want to verify now if that residual is satisfied or not. If it's not satisfied, well, we are in trouble. We need to make that equal. So let's call residual energy equation. And here we're going to say it's, and that will be for each section. So enthalpy out is this one, enthalpy in is this one, and the Q that I have is this one. Delta Z is here, remember, is out minus in, so it should be a positive number. And the mass flow, which is here. Okay, so the residual here is actually not 0, it's 12, and for all the other sections is not satisfied. Sometimes it can be positive, sometimes it can be negative. That means that the temperatures that were assumed before using this linear trend are not, they are not correct. So the approach now is going to be to try to change these temperatures, this column, until these are going to 0. For that, I'm going to use the solver, but the solver, remember, only likes to have one cell to minimize or to drive to zero. So I'm going to make here define the total error or the sum of the errors that is going to be the sum squared. And why the sum squared? Because here you see you have some that are negative, some that are positive, and I sum this, it might be that this still gives me zero, but it still is not converged, the one in each section. So by doing the sum squared, I'm making sure that all of them that the sum of all of them, if it's zero, then each one of them will also be zero. Okay, so 537, let me save it. And then I apply the solver. I say, solver, please drive that cell to, can be zero, can be to a minimum. And by changing, I want to change the temperatures, okay, which are in C12 and C18. Now, note something. When I change these temperatures, then these properties are going to be changed, and then these pressures are going to be changed. So it's a relatively heavy process what we are doing here, because we are changing also the pressure calculations when we converge on the temperature. And that's very good. That's how it should be done. But it's a relatively heavy process because by changing this column, we are also changing this column. So like both of them have to converge at the same time. So we now try to solve. Okay, we run into trouble, and this sometimes happens because we have this interpolation function that causes problem. So we went to save and then close and then open the file again. And let's see if now it works. It still has the same information, solve. And you see here is the objective cell, 537, 489. So it's kind of working, it's reducing the error. 388. So sometimes this happens, and that has to do with this interpolation function, that every time if I change the input, the interpolation should calculate a new value. So the solver should wait for the interpolation to calculate a new value. Okay, sometimes it doesn't wait, and then it fails because simply don't get new numbers to calculate. Again, and when I try without the recording, it goes much faster. So I think the recording does something that makes the solution to go a bit slower. Okay, but now finally we're getting close to, now it's getting to values, very low values. Okay, now it finished. You see now all the energy conservation equation is honored. We have heat is always leaving the fluid for all positions. Okay, and actually it's increasing from bottom up. And then you see this is the final temperature distribution. And let's see how it is compared to the other case that we assume a temperature of 50 at the wellhead, and we did a linear interpolation. So that's my solution now. Let's compare with the other one. Open the page. Okay, that's doing the energy conservation equation, and this is simply assuming a linear trend between 50 and 100. Okay, you see that it's now it's very different. Now it gave you a temperature of 65 instead of 50. But you see that the pressure at the bottom is actually not that different. So it's only 5 bar difference, which is less than 2% difference between these two. Okay, so this temperature in this case didn't do much difference on the pressure calculation. It does a difference in the pressure at each position. You see here 39 to 44. Here it changed maybe 10%, okay, but at the end that variation is only 2% on the bottom hole pressure. Another thing which is interesting to look at is the transverse plot of pressure and temperature. So this is now the pressure, and you see the temperature, and the change is not linear, but it's actually curved. And that has to do with the fact that the delta, what is driving the heat transfer in each position, is different. Like so the heat here is much less than the heat that you have at the surface.